So let's take a look at esters. Esters are things that we've all had some experience with, but we may not know we've had experience with. They're responsible for that smell with nail polish, and they often have a really sweet smell. Also, the banana flavour, the banana lolly smell. So any of those really sickly sweet smells are generally thanks to esters. So if we take a look here at the ester functional group, we can see that we've got a double bond O on one carbon, and right next to it we have an oxygen. So the carbon, it would look like this, so we'd have a double bond O and then directly bonded to an oxygen, and then both of these, the carbon here and the oxygen here, are bonded to a carbon chain. So it could be a methane group or an ethane group, a benzene ring, any sort of carbon chain. Now, the esters can be what we call hydrolyzed, so we can add water back into this bond here, and we will get the acid forming and the alcohol reforming that the ester formed from. So an ester is made from combining a carboxylic acid and an alcohol, and we do this through a process called condensation, and we generally do this through reflux. And we'll do it through reflux because we want to speed up the rate of reaction without losing any of our compounds. So if we take a look at this one here, we've got a carbon chain that is 8 long for our alcohol, so we can see our OH functional group at the end here. So, and that would then make this octanol. And we can see on the other side we have ethanoic acid, so our carboxylic acid. Alright, so for this condensation reaction to occur, we need to have this part collide. And we need to do that without losing any of our reactants. So our reactants in this case being octanol and ethanoic acid. So we need to reach our activation energy. So EA needs to be achieved. And we need to have successful collisions. We need to have these two parts colliding. To make sure that that happens in a reasonable period of time, we do that through something called reflux. And we do that in a condenser so that we don't lose any of our reactants out of the condenser. So we're increasing the frequency of our collisions to increase the number of successful collisions. So we need to have the right orientation, so therefore if we have more collisions, we're more likely to have more successful collisions with the right orientation. So if we get these two to react and have successful collisions, we will end up producing the ester octyl ethanoate. So in terms of naming that, we can see here we're now missing the two hydrogens and one of the oxygens. So if we were to split down here, we can see that this is where our carboxylic acid has come from, and this part is our alcohol. And we can see that we've got the ethanoic acid and our octanol on this side. So naming our esters, we have the alcohol part first, but we put a YL on the end. So in this case, we would have octanol, and we put an OA at the end of our carboxylic acid, so it would be ethanoate. And here are some examples below. So if we were to draw our line down here, this side we've got butanol, so that's why we've got our butyl, and on this side we have methanoate. So similarly, you can see with the next one, if we draw the line through the O, we can see the alcohols on this side, the carboxylic acids on this side. So this one is ethyl butanoate. And finally, with the last one, so if we take a look here, we've got 1, 2, 3 carbons, so propyl, and then 1, 2, 3, 4, so butanoate. Alright, so let's take a look at ester hydrolysis, which we can also talk about reversing esters back into the things that we made them with, so back into the alcohol and the carboxylic acid. So in acidic conditions, if we put the acid in and excess H2O, we can actually force the reaction back. So initially we put the alcohol and the carboxylic acid together to make the ester. If we add in excess water, we can add that water back, hence the hydrolysis name. So hydro being the water part, so hydrolyzing. And this is an equilibrium reaction, so we need to put in excess water. If we don't put in excess water, then we're not going to force the reaction in the direction that we want to. So putting in that excess water forces it towards the product side, in this case being the carboxylic acid and the alcohol. So we're going to get them to split back. The basic conditions gives us a complete reaction and not an equilibrium reaction. So if we hydrolyze our ester with sodium hydroxide, so aqueous sodium hydroxide, we're actually going to get the carboxylate salt and our alcohol. So of course we could then get the carboxylate salt and add acid to it, which would then form the carboxylic acid again, and the sodium would go back into the water solution. So we could add that acid back in and get a precipitate of our salt, depending on how big the carboxylic acid is. So let's have a go at working out what our products of acidic and basic hydrolysis would be for these esters. So we've got ethyl butanoate here and propyl butanoate. So let's have a go at the acidic conditions for ethyl butanoate. So remember, we've got excess water in acidic conditions. So let's split this so that we know this side then is our alcohol and this side's our carboxylic acid. So what we'll end up with is butanoate. So we're going to end up with we're going to end up with butanoic acid. So it's acidic conditions. So we're not going to get the iron because we'll actually add that hydrogen back on. So that's our acidic conditions. Alright, so we've got butanoic acid here as one of the products, and the other ethyl, so we're going to have ethanol. So ethanol is formed as well. Okay, so what about in basic conditions? So the main difference is going to be that instead of having the carboxylic acid, we're going to have the carboxylate salt. So we're going to end up with sodium butanoate. So we'll end up with sodium butanoate if we're using sodium hydroxide, or if we are using a different base, then it's going to have a different metal as part of it, but we will still get that carboxylate ion. We will also get ethanol produced back because that's the alcohol. Have a go at propyl butanoate and the two different products under acidic conditions and basic conditions, and test yourself. So pause it now, have a go at drawing them up, and then check your answer. So under acidic conditions, we've got propyl being the alcohol part. So we draw our line down the oxygen, we've got the 3 carbons, so we'll get propanol. And on the other side, we've got butanoate, so again we're going to get butanoic acid. And similarly, under basic conditions, we're going to get the butanoate ion and we're going to get propanol. So if we had sodium hydroxide and not an undefined base, we could have sodium butanoate. But if we don't know what the base is and we're just given a general OH, then we have the iron.